So in lesson 3.6, we're going to go through something called direct variation. And to kind of get through that concept, we're going to think about exchange rates. So if you've ever dealt with exchange rates before, when you go to a different country, you are going to convert our US dollars to whatever form of currency they use. And so it's going to vary from country to country how much you're going to get for that specific amount of money you exchange. So we're going to specifically work with rubles, which is going to be the Russian form of currency. So if we have $1 US in 2016, I believe this was the exchange rate, $1 US got you 5.84 rubles. So every single dollar you exchanged got you this much in the rubles currency. So as a conversion factor, we have 58.4 rubles is exactly the same as $1 US, which is our conversion. So these are exactly the same. This just equals 1. Okay. So we're going to make a table to kind of see if I exchange this many US dollars, what is going to be the currency that I'm going to get. So first and foremost, when we have no dollars, I'm not going to get any rubles in return. I can't just magically get money. If I have 10 US dollars, we're going to times this by this conversion factor. We get 58.4 rubles per $1 US. So the US dollars cancel, and you get 584 rubles. Okay? So basically, these dollars units cancel. So 10 US dollars gets you 584 Russian rubles. You do the same thing for 20, you would multiply this by 58.4, and you'd find out you get 1,168 rubles. For 30, same thing, you would take 30 and times it by 58.4. Okay? And so that will give you 1,752 rubles. Same thing for 40, you take 40 times it by 58.4, and you get 2,336 rubles. 50 times the 58.4, you would get 2,920 rubles. Okay. So we're going to make a graph based on this information. So on the x-axis, we're going to put the dollar amount that we're going to exchange. And then on the y-axis, we're going to see how many rubles do we get in return. And we'll do our best to graph this accurately. So we've got 0 US dollars. Let's make this 10, 20 bucks, 30 bucks, 40, and 50. And so if we look back, the most rubles we have is a little less than like 3,000. So I'm going to go up by 400s. So this will be 400 rubles. Skip 2, that'll be 800, 1,200, 1,600, 2,000, 2,400, 2,800, and 3,200. Okay. So we're going to plot all of our points. When we have no US dollars, we get no rubles. For 10 US dollars, we're at 584. So that's somewhere around right here. For 20, we're at 1,100 and some, which is around right here. 30s at 1,700. 40 is at 2,300, so it's close to the 2,400 range. And 50 rubles is at 2,920, so right around here. So if we look at the line, we're going to get this line giving us the exchange rate between US dollars and rubles. Okay. So we have the picture for our graph. What we want to do is we want to figure out what is the slope of the line of this graph. So you can take any 2 points you want. I'm going to pick that first one, 0, 0, because it's really easy. And then I'm going to pick the point when we have 10 US dollars, we have 584 rubles. So remember, to find the slope, you look at the difference in the y values, and you've got to keep the same order. So we'll start with the 584. We'll subtract the y value. And then you're going to divide by the difference in the x values. And you started with the 584 first, so I'm going to start with the 10 first. So we divide it by 10 minus 0. So this is equal to 58.4, which is exactly our conversion rate. So the slope of our line is just the conversion rate between these two currencies. Okay? So with that, we're able to actually create that equation. Remember, to write a linear equation, you need that rate of change, and you need that initial starting value. So in this specific instance, we're going to let y be the number of rubles. So y is going to equal 58.4 x, where x is the number of American dollars. And the initial starting amount is 0. So you don't really need that plus 0. It's just 58.4x. So the input is going to be American dollars or US dollars. So this is our x. And the output is going to be rubles. So that is our y value. Okay? So if we want to figure out what the current cost of a Big Mac is in Russia, Big Mac at the time was $2.15 in America. So the amount of rubles would be y equals 58.4 times the US dollars. So it's $2.15. So the amount of rubles a Big Mac would cost is $125.56 rubles. Okay. So it's $2.15 for a Big Mac. It would be 125.56 rubles. Okay. So this is our exchange rate. And exchange rates work just like you'd expect them. So if you exchange 0 US dollars, you're going to expect you're going to get 0 rubles in return. Okay? You're not just going to magically get money for nothing. If we doubled the amount of dollars we're exchanging, we would expect that the amount of rubles doubles as well, because it's the same amount of conversions. So it should double. And if you look back to our table, it is going to do exactly that. When you have 10 rubles, it's 584. When you double the amount to 20, the amount of rubles doubles as well. So you can look at that specific example to see it is true. So 10 US dollars is 584 rubles. And when you double the amount to 20, it doubles the amount of rubles, and you get 1,168 rubles. Okay. If you triple the number of dollars, the number of rubles should triple. And if you look back on the chart, you're going to see that, yes, that's true again. When we have 10 US dollars, you still have 584 rubles. And when you triple the US dollars to 30, you're going to have 1,752 rubles. So that's 3 times the amount. Okay. If you cut the number of dollars in half, again, it's going to do exactly the same thing to the amount of rubles. So it should get cut in half. And you can use either of these examples. This one down here. You start with 20 and you have 1,168 rubles. When you cut it in half to 10, it cuts the amount of rubles in half. Okay. So you can really use this exact same example, okay? Just reversing what you're starting with. So this is the idea of direct variation, or two quantities varying directly. When one doubles, triples, quadruples, the other is going to do exactly the same thing. So this is going to be our idea. When one quantity is found to simply by multiplying a second variable by a constant, we say these two quantities vary directly, or that they're directly proportional. So this type of relationship is called direct variation. So there's a direct connection between the two things. What one does, the other does exactly. So there's kind of some key distinctions for knowing whether two things vary directly. Algebraically, your equation is going to be y equals some constant times x. So there's no initial starting value. You start at 0. When you have none of one, you have to have none of the other. So an example would be y equals 3x. So if you look at this numerically, when x equals 1, y equals 3. When you double the amount of x, it doubles the amount of y. Triple the amount of x, triples the amount of y. And likewise, there's that same relationship going on. The key thing graphically is this has to go through that origin. It has to go through 0, 0. Because if you have none of one, you're going to have absolutely none of the other. There's no difference between the two. If you start at anything other than 0, it's not going to vary directly. Okay. So in the group work, we're kind of look through some examples. Before we kind of went through when we were dealing with writing these linear equations, we dealt with a cab ride. You had an initial charge of $5.10, so that was kind of your fixed fare, and then it cost $2.60 per mile. If you want to think of this, we want to see if this is an example of direct variation. So the key is, if you remember the cost, or you try to write some linear relationship between the two, the cost was that starting value, $5.10, and you added $2.60 per mile. So C was the cost, and M was the number of miles. If you look at this equation, we've got a problem here. You don't go through 0, 0, so that's one reason why this isn't a direct variation. And also, you don't have the form that it's some constant times the variable. So there's two reasons that no, this isn't direct variation. The first being, this starts at, when you have no miles, you have that $5.10 fixed fee. But it must go through zero, 0 for direct variation. And the second is this doesn't have the form where C is equal to some constant times the input value. So immediately you can write this off. It's not going to be direct variation. Okay. So let's instead look at a different example. We're going to talk about buying gasoline. So do you think the amount spent in a gas pump and the number of gallons purchased are quantities that vary directly? So again, remember the key is this has to start at 0, 0. So if I buy no gallons of gas, it's going to cost me no dollars. So I am going to go through 0, 0. If I buy 5 gallons, it's going to cost me whatever price it is, say $2 per gallon. And then if I buy double the amount, it's going to double the price because it's still the same amount for every single extra gallon you purchase. So yes, we do expect this to be direct variation. So you pay $0 for 0 gallons, and the cost increases by a constant multiple for each gallon you purchase. So you have a fixed fee that you're going to pay for a gallon, okay? So now let's say you stop in the local gas station to buy an energy drink, but you don't pump any gas. So how much would you pay for 0 gallons of gas? Well, you didn't buy any gas, so you're still going to pay $0. Now, if we buy 5 gallons of gas and it costs us $11.10, we want to see how much would you expect it to pay if you double the amount to 10 gallons. So 5 gallons costs you $11.10. When we double the amount of gallons, we're going to expect that the price is going to double. So the price would be 2 times the $11.10. So if we paid $11.10 for 5 gallons, we're going to expect the price will double to $22.20 for 10 gallons. Okay. If instead we've got 5 gallons of gas for this price, if we cut it in half to 2.5 gallons, we're going to expect the price is going to do the same thing. So I'm going to decrease my gallons in half. The price is going to decrease in half. It would be $5.55 for 2.5 gallons. Now if we go to something a little bit more complicated, what if we have 15.2 gallons? It's not as simple because I can't just multiply the 5 by something to get 15.2. Can't think of that off the top of my head. So in this case, we're going to use that direct variation. So we learned about proportions. We can really set this up using a proportion. So we know that 5 gallons of gas cost us $11.10. And we want to see 15.2 gallons cost, we don't know, so let's say X dollars. So we're going to go ahead and set up a proportion between these two. So it's $11.10 for 5 gallons. We don't know the price, that's what we're calling X, but we know it's 15.2 gallons, okay? So basically this expression over here would give you the price per gallon, but these proportions should be exactly the same. If you boil it down, it'll give you the unit rate for that gallon of gas. So to solve this, we go ahead and we cross multiply, or really, because I have the X up top, if I multiply this side by 15.2 and I do the same over here, we can solve for that unknown X. So the 15.2's cancel, and we're going to get 15.2 times 11.10, that'll be 168.72 over 5 is going to be the price for the 15.2 gallons. So X is going to be around 33.74. So it's $33.74 for 15.2 gallons. Okay. All right, so let's see now how we can come up with some type of equation to represent this direct variation. So we're going to let C be the cost of buying G gallons of gas. So the cost is dependent upon the amount of gallons. So the direct variation we'll set up is the cost is equal to some constant times the number of gallons. And what we want to do is we want to solve for this constant K. We know that 5 gallons cost $11.10. So this is our value of G, and this would be the value of C. So 11.10 is equal to K times 5. And this will allow us to solve for the constant K. So we can go ahead and divide both sides by 5. So these 5's cancel, and we get K is equal to $11.10 divided by 5. So that's 2.22. So we can write our variation equation. The cost for G gallons of gas is 2.22 times the number of gallons. Okay. All right. So this constant is 2.22. So what that is this is the cost per gallon of gas. So it's $2.20 per gallon. So now if we want to figure out how much we're going to pay for 15.2 gallons, we could really use this equation instead of setting up that proportion like we did before. So the cost is 2.22 times the number of gallons. So for 15.2 gallons, we would take 2.22 and multiply it by 15.2. And again, with rounding to the nearest penny, this would be 33.74. So it's the same thing. We'd expect to pay 33.74 for 15.2 gallons of gas, which is exactly what we came up before. But it's a lot easier to write this equation to talk about what's going on, because now for this next problem, when I want to figure out for all these different prices, we could just plug it into this formula instead. So the equation allows us to plug things in easier. So the equation lets us quickly plug in each value for J. So that's the benefit of coming up with this equation. So now we want to fill out this table based on these different gallon price or gallons. We want to see what is the cost. So every single time, we're just going to plug in the value of G to figure out the cost. So if you get no gallons of gas, let's erase this just to make it easier. The cost will be 2.22 times 0. So it's $0 for 0 gallons of gas. When you get 3 gallons of gas, it's 2.22 times 3. So it'd be $6.66 for 3 gallons. For 6 gallons, same thing. Multiply the 222 by 6, and it would be $13.32 for 6 gallons of gas. Likewise, you're going to just take 2.22 times it by 9, 2.22 multiply it by 12, and then multiply by 15. And you're going to find out it would be $19.98 for 9 gallons. For 12 gallons would be 26.64, and then for 15 gallons, 33.3. Okay. So we can do all of the odd pieces now. So if we want to put $11.55, or if we want to put $11.55 gallons into our car, we can figure out the cost. So the cost would be $2.22 times the number of gallons, which is 11.55. So if you round this to the nearest penny, it would be $25.64 for 11.55 gallons. If we want to reverse it, if we're told we spend $40 and want to know how much gallons, instead in this equation, I'm given the cost, so I'm going to plug the 40 in for C. So the 40 is equal to 2.22 times the number of gallons. So if you want to solve for G, you've got to divide by 2.22, so those cancel, which means you have to do this over here. So you're going to find out that 40 divided by 2.22 is about 18.1. So the number of gallons is 18.01. So if we spend $40, we know we've put 18.01 gallons in our car. Okay. So this is kind of a nice way to solve equations. It's a little bit easier than the stuff we've learned before. So when you have direct variation, you've got that form y equals kx. The initial value is nothing because when you have none of one, you have none of the other. So given some quantities that vary directly, you're going to use that specific information to find this constant of variation k. You then can rewrite it in that form where k is whatever number you find, and then you can go ahead and manipulate that as necessary. So let's try some more examples. If you get paid hourly at your job, the total amount of money you earn varies directly with the number of hours you work. So if you work no hours, you're not going to get paid. So let's say you worked 14 hours last week and made $163.80. We want to write a variation equation describing your total pay P in terms of hours worked. And then we're going to see how much would we make if we work 20 hours and how much would we make if we work 25. So because there's that direct variation, we know our pay, which is P, is some constant, which will end up being our hourly wage, times the number of hours we worked. Okay? So we're given some information. We're going to make 163.80 for 14 hours of work. So when H is 14, P is 163.8. So to solve for that constant of variation, you divide by 14. So that tells us that K is going to equal 11.7. So basically you're going to get $11.70 per hour. So our pay is 11.7 times the number of hours we work. So if we work 20 hours, the pay will equal 11.7 times 20. So for 20 hours, you're going to make $234. for 25 hours. The pay is 11.7 times 25. So we would make $292.50 for 25 hours. Okay. So now let's go ahead and work with kind of more abstract equations. We want to solve the general direct variation equation, y equals kx, for k. So we've got y equals kx. If we want to solve this for k, we need to get k on its own. It's being multiplied by x. So let's divide both sides by it. So this way they cancel. So we're going to get the constant k is the output divided by the input. So what does this tell us about the ratio involving x and y? So basically that just is going to be the constant. So the ratio of y to x is always constant. For direct variation. Because the idea is y and x are arbitrary. This is always going to be a fixed constant between these two. So there's some very good advantages to using this direct variation as opposed to setting up some type of proportion. So if you want to set up a proportion, it's going to work, but you're going to have to repeat that for every single time you want to solve a problem. So if I'm going to change the proportion slightly, I've got to resolve a new equation. If I use this direct variation, I immediately know the equation involving the two, and it's going to be quicker to solve. So you never actually get to see the conversion factor you use either when you use a proportion versus a direct variation. So if you think of that gasoline problem we did quite a while ago now at this point, when we set up a proportion, all I ended up figuring out is how much it cost for 15.2 gallons. It doesn't tell me my cost per gallon. But when we set up this direct variation, I now immediately know if I have 1 gallon of gas, the cost is $2.22. So now I immediately get to know my conversion factor from this type of equation. Okay. So let's try a few more examples. We're going to get a birthday gift, so this is actually one of the authors here. He got a miniature bobblehead of himself for some reason. But what it is, we're told that the ratio of the actual size of the person to this bobblehead is 1/13. So the idea is I took my normal size and I'm going to get 1/13 of it, and that's going to be the height of my little bobblehead. So we're told that the mini-me is 5.82 inches tall. We want to see how tall the human is. We can set it up using a proportion. We can set it up using a variation equation, whatever it is. So in this one, we're not going to be able to necessarily set up a direct variation. So I think a proportion will work a little bit better for this particular instance. So we're told that $1 is 1/13 the real size. Okay. And so the doll is 5.82 inches. And we want to know the real size. Okay. So we're keeping the doll information up top, the real size on the bottom. So if we go ahead and we cross multiply, we're going to get that x times 1, which is just x, is 5.82 times 13. So that's going to be 75.66 inches. Okay. So the real person is 75.66 inches tall, which is about 6 feet and 4 inches. I think that's the right notation. Okay. But basically the idea is I took my normal size, I divided it by 13, so I scaled it down by 1/13. Okay. So I just had to multiply the doll's height by 13 to get back to my original. Right? Now we'll do the same type of thing. We're told the mini-me from Austin Powers movie is 32 inches tall. So if he had a bobblehead made at the same scale as ours was, we want to figure out what his height would be. So this is his actual height. 32 inches is how tall he is. We're scaling it down by a factor of 1/13. So I'm really just going to take this and divide by 13. That's going to be the height of the doll. So this is going to be about 2.46 inches. So the height of mini-me in bobblehead form would be about 2.46 inches. Okay. All right, so now let's work with a sales person. The sales commission earned by a saleswoman varies directly with her gross sales. In one quarter, her commission was $7,200 on $180,000 in sales. So basically, when she goes and she sells all of this furniture, whatever it is, she's going to earn a percentage of that sales, and that's going to be her commission. So from $180,000 in sales, she gained $7,200. So if we want to see her commission rate, we need to see how much is the $7,200. What percentage of 180,000 is that? So we're going to take this 7,200 and divide it by 180,000. So she made 7,200 out of the 180,000. So if you do this division, it's 0.04. So remember, as a percentage, you would move that over twice. This is exactly the same as 4%. So she's going to earn 4% of her gross sales. If she doesn't sell anything, she's not going to make a commission. So that's an example of direct variation. So now we can create an equation involving that. We're going to let C be how much commission she's making. And we're going to let S be the gross sales. Okay. So her commission is 4% of her gross sales. So we're going to take the S and we're going to times it by 0.04. So now, based on all these different gross sales values, we can figure out her commission. And we're just going to use this equation. So her commission will equal 0.04 times her gross sales, which is 40,000, because she's getting 4% of the 40,000. So she's going to make $1,600 in commission. If she sells 80,000, her commission will be 0.04 times the 80,000. So she'll make $3,200. For 120,000, we do the same thing. We're just going to keep multiplying this number by 0.04, and she's going to get $4,800 in commission. So likewise, if you take 160,000 times it by 0.04, you're going to get 6,400. 200,000 times 0.04 is 8,000. 240 would be 9,600. And then if you keep doing this process, you're going to take each and every one of these and multiply it by 0.04. You'll get 11,200. You'll get 12,800. And finally, if she sells $360,000 worth of product, she'll get $14,400 in commission. Okay. All right. So earlier we observed that as the number of rubles goes up, so does the number of dollars. And we also saw the amount of gas you buy goes up, so does the cost. So is this always going to be the case? If the constant of variation is negative, what effect does it have on y if y increases? And we want to explain. So we want to think about the generic equation that describes this. So basically what this is saying is we have this direct variation, but we know this constant is going to be negative. So this value of k is negative. So still, if you have no x's, you're going to have no y's. But now as x gets bigger and bigger, because this value of k is negative, y isn't increasing, it's getting bigger in the negative direction. So here, in this case, as x increases, y decreases. Okay? Because you can think of some examples. Think of y equals negative 2x. If you pick some points, so some x and y values, when x is 0, y is 0. When x is 1, y is negative 2, so the value is decreasing. When x is 2, y is negative 4, so it's just decreasing constantly. Okay, so it's still kind of an example of direct variation. It's just having this opposite effect. So we're going to look at some different graphs and then we'll end it here. We want to see if this illustrates a situation where y varies directly as x. And we want to explain our reasoning behind it. So if you look at these three, we've got kind of some key things. This 23 and 25 both go through the origin. So when you have no x's, you have no y's. But in this case, we don't go through the origin. So when I have no x's, I'm still starting at something. So this isn't a case that we have direct variation. So in this specific one, no, it's not an example of where y varies directly as x, because it does not go through 0, 0. Okay. But in both of these cases, 23 and 25, yes, they are direct variations. It goes through 0, 0. And is a straight line. So there's a constant relationship. Between the two. Okay. And then the same thing for 25. It goes through 0, 0, and it forms a straight line. So it is an example of direct variation.